Hi and welcome back to class of Design of Machine Elements. I am Hitesh Raiyani, Assistant Professor at LJ Institute of Engineering and Technology. This is lecture 20, Thick Cylindrical Cells. The learning outcomes of these lectures is to learn the thick cylindrical cells. But before we start the thick cylindrical cell, we complete the worksheet problems given in previous lectures. So consider the worksheet problems given in previous lectures. A seamless spherical cell 900 mm in diameter and 10 mm thick is being filled with the fluid under pressure until its volume increased by 150 into 10 raised to 3 mm cube. So here a seamless spherical cell is given and diameter of cell is 900 mm and thickness of this cell is given 10 mm and fluid is filled in this pressure vessels until the pressure increased by 150 into 10 raised to 3 mm cube. So calculate the pressure exerted by the fluid in this cell and taking the modulus of elasticity for the material of cell is as 200 kN per mm square and the Poisson's ratio as 0.3. So here the spherical cell is given and the pressure is, we have to given the delta V because it is given the volume increased by 150 into 10 raised to 3. That means delta V is given and diameter of cell is given 900 mm, T is given 10 mm and E is given 200 kN per mm square and Poisson's ratio nu is given 0.3. And we have to find the pressure intensity or pressure exerted by the fluid in this spherical cell. So first of all we collect the data given in these problems, that is D is equal to 900 mm, T is 10 mm, delta V is 150 into 10 raised to 3 mm cube, E is 200 into 10 raised to 3 Newton per mm square. We converted into kilonewton per mm square into Newton per mm square and U is given 0.3. Here delta V is given, so we have to use the equations delta V is equal to pi into P into d raised to 4 divided by 8PE into 1 minus mu. Here delta V is given 150 into 10 raised to 3. So we have to place delta V is equal to 150 into 10 raised to 3. Now we have to calculate the pressure exerted by the fluid. So in these equations you can see we have to find the P, value of P. So if you see in these equations there are D that is given in problems 900 mm, there are T that is 10 mm, E is the modulus of elasticity, it is given 200 into 10 raised to 3 Newton per mm square and there are nu that is given 0.3. So if we place all these value in these equations, we get equations like that is delta V is 150 into 10 raised to 3 is equal to pi into P into 900 raised to 4 divided by 8 into 10 into 200 into 10 raised to 3 and into 1 minus 0.3. And if we simplify these equations to calculate the pressure exerted by the fluid, so we get the answer of pressure exerted by the fluid according to our condition, that is 1.66 Newton per mm square. Now consider the thick cylindrical cells subjected to internal pressure. So here we have to discuss the thick cylindrical cell subjected to internal pressure. So consider the thick cylindrical cell as shown in figure A. Figure A shows the thick cylindrical cells. Here the pressure is exerted P, that means the pressure intensity is P and it is subjected to internal pressure as you see in the thick cylindrical cells, and there Ri is the internal radius of particular cylindrical cells and Ro is the outer radius of the cylindrical cells, and if you see that there are T is the thickness of this particular cylindrical cells, and there are taken one cross section dx at the radius x. So we have to consider this thick cylindrical cell to subject point of view, And if we seen that in previous thin cylindrical cells, we assume that the stress distributions of cells is uniform throughout the cross sections, or here in thick cylindrical cells we cannot consider that the stress is distributed uniform throughout the sections. So here the stresses varies according to the thickness of cylindrical cell. So consider the figure P, that is the tangential stress distributions and subjected to internal pressure P. You can see in this figure there are internal pressure is applied P, and if you see the stress distributions curves throughout the thickness of this cylindrical cell, you can see that there are tangential stress maximum at the inner radius of these cylindrical cells, and it is gradually decreased as we go from inner to outer surface of the cylindrical cells, and it is minimum at the outer surface or outer radius of cylindrical cells. So there are sigma T max at the inner surface or inner radius of cylindrical cell, and sigma T minimum is equal to AH is at the outer surface of cylindrical cells. So here are stresses gradually decrease, and you can see the in figures. Now consider the radial stress distributions. Same as tangential stress distributions here. In radial stress distributions, there are maximum radial stress at the inner surface of the cylindrical cell, and it gradually decreases and it becomes the zero at the outer surface of the cylindrical. So if you see that here the radial stress is in compression mode, so it is in the downward direction. So here the radial stress sigma r is maximum at radius ri, and sigma r is minimum and at outer surface of cylindrical cell, and it is zero at the outer surface. Now in thick cylindrical cells, we have to follow the equations according to the Lamb's equations, Bernoulli's equations, CLAVARINO'S equations, and Bernoulli's equations. These four equations we have to use in design of thick cylindrical cells. So these equations we have to use to design the thick cylindrical cell according to the conditions of materials and the end connections. So according to the material of cylindrical cells and end conditions of pressure vessels, we have to use these four equations to design the thick cylindrical cells. So first is Lamb's equations, Bernoulli's equations, CLAVARINO'S equations, and Bernoulli's equations. So these four equations is mostly used in thick cylindrical cell. Now consider the thick cylindrical cell as shown in figures here. The Ri is the inner radius of cylindrical cells, Ro is the outer radius of cylindrical cells, and according to the cylindrical cells, if we consider, then let us, the Ro is outer radius of cylindrical cell, Ri is the inner radius of cylindrical cell, T is the thickness of this cylindrical cell, and if you see that there are T is nothing but the Ro minus Ri. P is the internal pressures or intensity of internal pressures. Nu is the Poisson's ratio, and sigma T is the tangential stress, and sigma R is the radial stress. Now, according to the Lamb's equation, first is the Lamb's equations. According to Lamb's equations, the tangential stress is at any radius x is given by sigma T is equal to Pi into Ri square minus Po into Ro square divided by Ro square minus Ri square plus Ri square into Ro square divided by x square into Pi minus Po upon Ro square minus Ri square. So this is the tangential stress at any radius x according to Lamb's equations. And if you see the sigma r, it is the radial stress at any radius x. that is Pi into Ri square minus Po into Ro square divided by Ro square minus Ri square minus Ri square into Ro square divided by x square into Pi minus Po upon Ro square minus Ri square. So this is the tangentials and radials equations. We have to use these equations for the thick cylindrical cells. And if you see the tangential stress distributions here in figure, you can see that there are maximum stress at inner surface and minimum stress at the outer surface. So, and this cylindrical cell is subjected to internal pressure, as we seen in, as we mentioned in our slide, that thick cylindrical cell subjected to internal pressures, and here also you can see the internal pressure P is applied in this cylindrical cell. So we have to place the boundary conditions in this above equation. So here Pi is equal to P because we have to apply the P, that is the intensity of internal pressures, and there are no any external force, so we have to place the PO, that is the outer pressure, external pressure is equal to 0. Now if we apply these boundary conditions in above equation, then sigma T becomes P into Ri square divided by Ro square minus Ri square into 1 plus Ro square divided by x square. So this is the equations of tangential stress according to our condition, that is the internal pressure, say a cylindrical cell subjected to internal pressure. So this is the sigma T equations, and if we see in figures, there are maximum tangential stress at the inner surface, that is the R at radius Ri. So we have to find the maximum tangential stress, and for that we have to place the value of x is equal to Ri. So if we place in above equations x is equal to Ri, we get the maximum tangential stress, that is sigma T max is equal to P into Ro square plus Ri square divided by Ro square minus Ri square. So this is the maximum tangential stress, and it is derived by placing x is equal to Ri. And if we see in figures, there are tangential stress is minimum at the outer surface of the cylindrical cell. So to calculate the minimum tangential stress, we have to place the x is equal to Ro in above equations. So if we place x is equal to Ro, then the minimum tangential stress becomes sigma T minimum is equal to 2 into P into Ri square divided by Ro square minus Ri square. So this is the tangential stress, maximum stress and minimum stress. Now, if we consider the radial stress according to the Lam's equations like this, and if we consider the conditions of radial stress distributions throughout the thickness of cylindrical cell, and it is subjected to internal pressure, so we have to place the boundary conditions Pi is equal to P and Po is equal to 0. So above sigma R equations get simplified by placing the boundary conditions, and we derive the equations of sigma R by placing the boundary conditions is equal to P into Ri square divided by Ro square minus Ri square into 1 minus Ro square divided by x square. Here x is the radius at particular sections. So this is the general equations of radial stress according to our conditions. And if we see the radial stress distributions in graph or figures, there are maximum radial stress at the inner surface of the cylindrical cells and minimum radial stress at the outer surface of the cylindrical cell, and it is equal to 0. So if we see, we have to in figure to calculate the sigma R maximum, we have to place the value of x is equal to Ri in above equation. So we get the maximum radial stress is equal to minus P, and that is compressive. And minimum radial stress sigma R minimum is equal to 0. So you can find sigma R max is equal to minus P. it is compression. Now next is Bernoulli's equations. So this Bernoulli's equation is based on the maximum strain theory of failures, and it is applied for the open end cylinders, and according to the Bernoulli's equations, hole thickness of cylinder is given by T is equal to Ri into under root of sigma T plus 1 minus nu into P divided by sigma T minus 1 plus nu into P minus 1. So this is the equations of wall thickness of cylinder according to the Bernoulli's equations. In this equation, sigma T is the allowable stress, and nu is the Poisson's ratio, and P is the pressure intensity, and Ri is the internal radius. So in this case we have to take sigma T, that is the allowable stress, and that is sigma T. We have to take 0.8 times the yield stress, that is sigma y. So we have to take sigma T is equal to 0.8 into sigma y. Now third is the Clavarino's equations. The Clavarino's equations is also based on the maximum strain theory of failures, and here this equation is applied for the closed end cylinders, and according to the Clavarino's equations, the whole thickness of cylinder is given by T is equal to Ri into sigma T, T is equal to Ri into under root of sigma T plus 1 minus 2 nu into P divided by sigma T minus 1 plus nu into P minus 1. So this is the whole thickness equations according to the Clavarino's equations, and we have to use these equations whenever the condition is in closed end cylinder. And here you also have to take sigma T is equal to 0.8 times the yield stress sigma y. Now, and fourth and last is the Bernoulli's equations. The Bernoulli's equations is generally used for the high pressure oil and gas pipes, and these equations, according to these equations, the whole thickness of cylinder is given by T is equal to P into Rho divided by sigma T. Here sigma T is allowable stress, P is the internal pressure, and Rho is the outer radius. And here you have to take the sigma T values according to the material. So for ductile material, sigma T you have to take 0.8 into sigma y, and for brittle materials you have to take sigma T is equal to 0.125 into sigma u, that is ultimate tensile stress. So in these lectures we learn one worksheet problems given in previous lectures, and we learn the thick cylindrical cells and which are the equations used in thick cylindrical cells. Thank you.